the organizers have asked me to say a few words about my early time in Canberra before I start my scientific talk. So I arrived in, and these reminiscences are going to be in two parts. First, there's sort of a descriptive part of, what the department was like, and then there were some sort of unusual things, which I will mention, sort of anecdotes and things like that. So I arrived in Australia from Holland to be a postdoc with Rodney from 1986 to 1990. And we were based in the Department of Theoretical Physics in the research part of the campus. And the permanent staff of that department was Rodney Baxter, Kailash Kumar, Lindsay Tanner, Bill Woolcock, Bob Dewar, Jay Mahanti, and Brian Robson. And there was sort of a postdoc for each group. So Chris Hamer was there, Tuck Choi, I don't think has been mentioned before, he was there, Yoshi Okondo, Glenn Cantwell, Mukunda Das, Bruce Henry at some stage, and then myself. And students were housed in the basement, and one of them was Alex Ovcharak, who will be speaking tomorrow. Now, to make up for the fact that we were far removed from the international centers of mathematical physics, there was a continuous stream of international visitors. Michael Atiyah, Fred Wu, Jacques Berg, Vaughan Jones, Craig Tracy, Hans Kapel, Vladimir Korepin, just goes on and on. And the other thing which made the environment very productive was that on the other side of the campus, there was the math department and the Center for Mathematical Analysis, with which we had a lot of contact and more over the years. And the math department was led by Michael Barber, and some other people over on that side of the campus were, of course, Murray, Nalini Joshi, and, for instance, Gerard Heusken, who is now the director of Oberwolfach. Now, there were some things that struck me as unusual at the time, or maybe considered unusual now. First of all, was that at work, Rodney was always sitting behind his computer, doing what now might be called experimental mathematics. And at that time, this was very unusual. And also, Rodney, I think, removed all evidence of this from his published work. So he would use these experiments to find out what was going on. And once he knew what was going on, he didn't need the scaffolding anymore. Another thing which was very unusual to me is that there was a tea lady that came into our building every day, twice actually. So she would come in the morning and then make tea and serve tea, and then she would clean up and go home again, and then in the afternoon she would come back and make tea again. Now, of course, it didn't take long for the penny saving bureaucrats to change this situation, but it was good while it lasted. And we had a beautiful tea room overlooking Lake Burley Griffin. Now, another thing which I've actually never encountered since then was that the secretary Joan, when she didn't have any more work to do, she would come knocking on our doors to ask if we please had some work for her. It's a most unusual situation. And Rodney once told me that he considered hiring Joan his most important achievement as head of department. And now another thing which is maybe common in France, but certainly not in the Netherlands where I was from, is that every day we would have a hot lunch in the garden of International House, sitting in a nice setting in the sunshine, because actually Canberra is a very sunny place. And a lot of people, not so much from our department, but certainly other people would be having wine at lunch. So that was it was really a jolly situation. Now, every year, Rodney and Elizabeth would invite my family and myself to spend Christmas with them, which was wonderful because we didn't have any relatives in this continent. And at these Christmas dinners, there you would have the unusual sight of Rodney Baxter, the family man, with a silly paper hat on his head, and to add to the atmosphere. And you know, you have these things that you can open and then put on your head. Now, another person who was would come in from time to time to the school was Sir Mark Oliphant, who was the founder actually of the Research School of Physical Sciences, and who had played a very important role during the Second World War with the development of atomic weapons. And he had also been the governor of South Australia, but in the 1980s, he found himself living in what is called a granny flat in his daughter's backyard. So you see, this is that's the way where we all end up eventually. And then, well, finally, like most of us, or many of us at this conference, I would like to end my brief reflections by expressing my gratitude to Rodney for bringing me to this country. My Canberra years were very productive for me, and those years have provided a solid basis for a career of what Rodney would call doing my sums. So I will now start my talk about some sums that I have been doing recently. Okay. And the title is The Factorizability of Integrals of ODEs. And it's actually not just, I couldn't fit it all into the title. It's not just the factorizability of integrals, but also the factorizability of preserved measures. Let me see. So, now, this is all based on the theory of Darboux polynomials, which is one of the, well, inventions, if you like, of Darboux, who is a genius in my book. Anyway, but first of all, I have here a definition of a group of, or of a set of, a family, you might say, of systems, the Lotka-Volterra system, the quadratic ordinary differential equations, and they read xi dot as xi times ri plus the sum of aij xj. So here the dots denotes the time derivative, and well, of course, they were first found by Lotka and Volterra independently, and they describe things like fish populations in a pond in small dimensions, but they've been very influential in certain applied areas. Now, what is important is the most important definition I've got here on the slide is the definition of Darboux polynomials. So a polynomial P of x is a Darboux polynomial for the ODE dx dt equals f of x if there is another polynomial C such that the time derivative of P equals C times P. And since C and P are both polynomial, this is a non-trivial comment, because otherwise you could just define C to be dp dt divided by P, but then it would in general not be a polynomial. So by dp dt, I mean, of course, this is subject to x being a solution of the differential equation. So d dt is d dx times dx dt. And so as we will see that this will lead to factorization of integrals and of measures. Okay, so here are some properties of Darboux polynomial. Now this is all very elementary for those who know it, but I think a lot of people have never heard of Darboux polynomials, and certainly until about 10 years ago, I hadn't never heard about them either. So if a system has two different Darboux polynomials, P1 and P2, I don't think I mentioned it yet, but if we go back one slide, this C here in front has a dp dt equals C times P. That's called the cofactor of the polynomial P. So we have two different polynomials with two different cofactors. Then it's not difficult to work out that the time derivative of p1 to the power alpha 1 times p2 to the alpha 2 is alpha 1 times cofactor 1 plus alpha 2 times cofactor 2, and then times this original product. So that means that this is again, well, a Darboux function, because if alpha 1 and alpha 2 are not integers, then this is not a polynomial, but it is still a function. Then this is the cofactor of this new function. And more generally, if you have a product of a number of these, say alpha 1, alpha 2, alpha 3, etc., then that's a first integral if and only if the sum of these of alpha I times the cofactor ci equals 0. So we see that if we want to find a first integral, we need to find a linear combination of cofactors that is 0. And these cofactors indeed form a linear space, but the p's don't. The Darboux polynomials do not form a linear space. You cannot add p1 and p2. The whole point is you have to multiply them to get another Darboux function. If you add them, nothing. Well, you lose the properties. Okay, so here we have the cofactors form a linear space. That means that since we want a linear combination of cofactors to be 0, we're guaranteed that that will be the case if we have more cofactors than the dimension of the space. So if there's more Darboux polynomials than the dimension of this linear space, then there must be one or more integrals, and they will be products of powers of the Darboux polynomials. Okay, so now I'm going to give you a little outline. In the beginning, we will restrict to homogeneous quadratic differential equations. And actually, I'm going to talk mainly about Lotka-Volterra systems, because that's just easier to work with. But this holds more generally, most of what I'm going to say. So for homogeneous quadratic differentials, then all cofactors must be linear. So the space of the cofactors is n-dimensional. That means if we, in order to guarantee the existence of an integral, we need n plus 1 cofactors. And once we have that, then finding the Darboux polynomials is a linear problem. Well, I'll just skip this sentence. Our procedure, for constructing these super integrable ODEs will have two main, well, actually, I'm first going to show you how you construct a system with one integral, and later then you'll see that you can repeat this procedure to get as many integrals as you want. So and if you have sufficient number, of course, they're integrable. First, we have the large class of systems that always has at least n explicit Darboux polynomials. Well, that's the Lotka-Volterra systems, as you will see. And then the second ingredient is that we adjust the parameters so that we get some more Darboux polynomials. So that's sort of the outline of the procedure. So here again, I've got the Lotka-Volterra systems. And what I didn't mention in the beginning is that actually the beauty of these Lotka-Volterra systems is that these xi's, they can be regarded, so just the x1 to xn in n dimension themselves are Darboux polynomials. And because this says xi dot is xi times some polynomial, and then this polynomial that multiplies xi is then a cofactor for that for pi. So we can read this as this is a special example of pi dot equals pi times ci. So what that means is that we have now that these systems these Latkamp-Volterra systems all already have n Darboux polynomials and n associated cofactors. And what I mentioned before is that if you have n plus 1, because these might all be linearly independent. So I'm first looking at the case where all these Ri's are 0 at the homogeneous case. So if I look at the case where these n cofactors are independent, then we need one more Darboux polynomial with its cofactor to ensure that we will have an integral. And so we do that by showing that there is actually a linear combination of two xi's, say in this case xi and xk. In my examples, it will always be xi and xi plus 1. There are linear combinations which are also Darboux polynomials if we tweak the parameters correctly. And that's basically is the ingredient, I guess, that we have contributed. So I'm not going to give you examples immediately in n dimensions. I will start in 3 dimensions. And in all the examples, I will use this matrix. And this matrix has been constructed in such a way that for E and D here are just parameters that I'll tweak later on. And that for generic position of E and D, these 3 cofactors, because these are cofactors of x1, x2, and x3, or let's say the cofactor of x1 is minus 2x1 minus 1x2 plus E times x3. And similarly for the cofactor of x2, and x3. Okay, so we have these 3, but we need one more to guarantee an integral. And so if we tweak this parameter to be 2, then I'd make it 2 because there's also a 2 here. And that's enough for a linear combination of x1 and x2 to exist that is also a Darboux polynomial. And I'm not going to give you the details, but this linear combination we've got down here is 5x1 minus 3x2. Basically, 5 is 3 minus 2, and minus 3 is minus 4 minus 1. And so now we've got 4 cofactors, and we need a linear combination of them to be 0. So that means we need a left 0 eigenvector, and that left 0 eigenvector is given here. So it still can depend on D, and for arbitrary D, in this we've put E to equal to 2. This is the first integral that we can construct in this way. And these exponents are just these entries of the left 0 eigenvector. So to find this integral, all we had to do is a little bit of linear algebra. Had to find the left 0 eigenvector of a 3×4 matrix. And that is actually not a very difficult thing to do. Okay. Now I'm going to up the ante a little bit and go to inhomogeneous systems. So now we have in our original notation, we have we add linear terms that x1 dot equals r1 times x1 and then plus the quadratic part, and the same for x2 and x3. And we take all these linear parts to be the same. If we do that, then I construct a extended matrix, and where this first column or first row, sorry, denotes the cofactor of x1, which is 1 minus 2 times x1 minus x2 plus 2 times x3. And so taking this system and adding these linear terms, that just adds these ones here. But then, because the way we've chosen here is not just to put these both equal to 2, but also these are both equal to 3. And that allows us to have both a linear combination of x1 and x2, to be a Darboux polynomial, which we call P4 here. And there's also a linear combination of x2 and x3, which is P5. And this h is just 4 minus -4, and -7 is just -7 minus 2. Now we need a left zero eigenvector of this 5 by 4 matrix. And the left zero eigenvector is given here. Of course, on multiple, but that doesn't change things. Is also, and then it leads to this very simple, remarkably simple integral in 3 dimensions for the inhomogeneous case. And now the special thing is, if you look carefully, we see this the Darboux polynomial x1 and x3, and we see these combinations of x1, but we don't see the Darboux polynomial x2 entering here, and that's because there's a 0 here. And this is not a coincidence. This is actually a property of these of our special construction, and that turns out that many of the integrals will be of this kind of form. Actually, there will only be one that depends on all the Darboux polynomials that are being considered in general in higher dimensions. Okay, let's go. All right, so now I've shown you for the in 3 dimensions, both for the homogeneous and for the inhomogeneous case, how you can get one integral. I'm now going to show you how you get a preserved measure. Actually, for that, a preserved measure satisfies this equation. The density of the preserved measure, if you take the time derivative of that, that is going to be the divergence of the vector field times the preserved measure, if it exists. But that means that this m is a Darboux function, because it's dm dt equals some function of x times a scalar function times m. And it's actually, it turns out it's sufficient for this matrix A in the homogeneous case, for the matrix A in the Lotka-Volterra system to be generic. So to be that that it's an n by n matrix, that the determinant is non-zero. And so how do you show that? Well, we want linear combinations of the Darboux polynomial to be equal to the divergence. So if we put that here, that means that, let's see, what have I done here? The divergence of f is just m dot divided by m. And then the linear combination of the cofactors is ci is just the Darboux polynomial pi dot, the time derivative of the pi divided by pi. So then we have this equation. Well, that's, again, is undergraduate problem to integrate this. It just says log m is the sum of these, because plus a constant, but the constant can be ignored here. So that means that then m is just the product of pi to the beta I, where the beta I are the solutions of this. So I'm going to show this in an example, but in order not to get sort of bulky formulas, I've put some simple values for E and D. And we obtain this measure in terms of this density. This is the density of the measure in terms of x1, x2, and x3. And I think it's good to have a look at this. It wouldn't be so easy to find this by just guessing, right? Or even by some so where you tried all exponents, you'd have to try a lot of exponents before you got to this. And of course, this only gets more difficult in higher dimensions. Okay, so now in a sense the most difficult case. So now we will have well, no, that's not really true. The inhomogeneous case, well, it's the most difficult of the two, and it's also the most.
No sound.
What did you say?
Oh, sorry. Somehow we just lost the sound, but it's back. So.
Okay, good. All right. Well, I'll just start from the top again. So now we're going to do the 3D inhomogeneous example. This was my original matrix. For simplicity, I put this D equal to 2. And now, oh yeah, the beauty is, or the interesting thing, I now take two of these R's, so the linear terms to be 1, and the third one 2. So they don't all have to be the same. So that's special about this case, if you like. And then if we do that, then we get this product of each of the 4 Darboux polynomials to a power where this power has been computed in the way that I mentioned before. Okay. Now the beauty of all this is that all of these things that I've been saying remain true in n dimensions. So if I replace everywhere where before everything was in 3 dimensions, if I replace that by n dimensions, then all 3's become n, all 4's become n plus 1, and all 5's, which is here, becomes n plus 2. And then, so in n dimensions, let's take, say, this case, in n dimensions, this case, pointing with my finger, that doesn't help. In n dimensions, inhomogeneous, we need n plus 2 Darboux polynomials to guarantee 1 integral. And then n plus 3 to get 2 integrals, etc., etc. And as far as we are aware, these results for measure preservation seem to be new, and these results are formal, I should say. So now I'm going to go to the easiest case, which is the homogeneous case, and start again from this thing. Then we have 0 additional, so that we have no first integrals, but we do have a preserved measure. Then I calculated before, if we tweak E is equal to 2, we find 1 Darboux polynomial. But now if I tweak this D to be equal to 3, we actually can find a second integral. And this kind of idea works also in n dimensions. So in addition to the x1, x2, x3, x4, x5, and so on being Darboux polynomials, we will have linear combinations of x1 and x2, linear combination of x2 and x3, and linear combination of x3 and x4, etc., also being an integral. And so that is shown here schematically. Here, these 1, 2, 3 denote the xi, x1, x2, and x3, and then there's this link between them denotes the Darboux polynomial which is a combination of 2 and 3, and this line denotes a combination of x1 and x2. And the most general matrix, 3 by 3 matrix that satisfies that is the one where I just need these two to be equal to get a linear combination of x1 and x2 to be double polynomial, and a linear combination of these to be equal. I need these parameters to be equal to get a linear combination of x1 and x2 to be equal to be a double polynomial, and I need C1 these both to be equal as well to get a linear combination of x2 and x3 to be to also be a double polynomial. And so then we have 1, 2, 3, 4, 5, 6, 7 parameters. But in 4 dimensions, we can achieve this in 2 ways. And we can link 1 and 2 and 2 and 3 and 3 and 4, but I can also link 1 and 2 and then link 2 to 3 and 2 to 4. And they are associated with different matrices A. Now, so in 4 dimensions, there's 2 different ways of doing this, but the number of ways, or these trees rather, these are labeled by trees. In higher dimensions, this number of trees grows very rapidly. So here's the result. You can do this. Each tree will represent an integrable Lotka-Volterra system. Okay. Now there's some things that I didn't have time to discuss today, but we've shown that there's no simple connection between the systems represented by different trees. And we've also recently found a connection to hypergeometric first integrals. And then what I haven't discussed at all is the case that maybe of most interest to people in statistical mechanics is the Hamiltonian case. Here we have integrability that's either associated with measure preservation, for which you need in n dimensions n-2 integrals, or with no structure whatsoever, and then you need n-1 integrals. But all those 3 kinds of integrability exist in the Lotka-Volterra systems. So my take-home message for you is that using Darboux polynomials as building blocks, the construction of preserved measures and preserved first integrals is all reduced to simple linear algebra. Thank you very much. And here are some references.
Do we have any questions for Reinout? Just looking through the reference list here. But I particularly enjoyed your reminiscences about the old life in the department.
Yeah, I must say a lot of memories have come back thinking about this, things I hadn't thought of for a long time, and names.
Likewise.
Yeah, it's been good.
Yeah.
As Elizabeth Baxter said to me in our correspondence after I contacted her, is that was a happy and busy time, and so it was.
Yeah, it was indeed. So, are there any questions from the audience here? Anyone can cut in online as well. I think in this part of the world, we're all keen to eat lunch, I think now.
Well, for me, it's more coffee.
Okay, then, Reinout, so thank you for a wonderful talk.
Thank you.